Alright, hello. Welcome back to another physics lecture. We're on lecture number 4 now, and we're going to be talking about Newton's second law of motion. So in previous lectures we looked at Newton's first law of motion, which had basically all to do with inertia, the fact that objects with mass don't want to change the way they're moving. So if they're at rest, they want to stay at rest. If they're in motion, they want to stay in the same motion, uniform motion. And then we took a little bit of a sidetrack to look at just motion in general, that being, how we define the rate at which something changes its position, that being velocity. And whoa, excuse me. Yeah, so we talked about velocity, and then if you were going to change your velocity, so remember velocity wasn't just how fast something is moving, but also the direction that that thing is moving in. And if you change your velocity, that is what we call acceleration. So, and then we also talked a little bit about force in the past, and forces as being something that essentially just pushes or pulls on objects. So all that's going to come together somewhat in this lecture, where essentially we're going to try to answer the question, how does an object move when a force is acting on it? So again, a recap of Newton's first law, which was essentially that if there is no net force acting on an object, so remember the difference between a single force and a net force, the net force being essentially the total, if you sum up all the forces acting on an object, what's the net effect of all those forces? So if there's zero net force on an object, Newton's first law says that object is going to have a constant velocity. Or the same thing as saying that object is going to be in uniform motion. And that might even be, it has zero velocity, like at rest, it's still considered uniform motion. It's not changing its velocity. And then also we looked at the definition of acceleration last time, which was essentially how much an object changes its velocity over time. And so some of the kind of implications of Newton's first law was that, well, if there's no net force, or the net force we say would be equal to 0 on an object, then the velocity of that object, or the motion of the object, is not going to change. However, the opposite, or the inverse sort of that statement, is that if the net force is not 0, meaning there is an overall net force on an object, Newton's first law would actually imply that the velocity of that object would not be constant, which would also imply that that object is accelerating. If its velocity is not constant, that means, there you go, it's a definition of accelerating. So it's changing its velocity, so it's accelerating. So Newton's first law, you can look at it in a lot of different ways, but all of these things sort of imply each other. If you have an object, you notice an object and its velocity is not constant, meaning it's changing, then you can infer that, well, say that that object is accelerating, and you can infer that there is a net force acting on that object. Okay, so how does the force and acceleration relate to each other? Essentially, the net force acting on an object and the acceleration of that object, meaning how much it's changing its velocity, are proportional. So if you act, and I'll just talk about it as a single force for a while, because it's a lot easier than saying net force every time, but in this, whenever I say this force, I'm meaning like the sum total of all the forces together. This is what they amount to, is just this force on an object. So like in the case of this soccer ball in the picture here, technically there's the force of gravity that's pulling down on the soccer ball. There's the support force from the ground that's holding the soccer ball up. But the net effect of those things is to be no net force there. The only real force going on in these pictures is the force of the foot, or the foot pushing the soccer ball. Right? So in this case, the only force to really talk about that really is concerning is the force from the foot. Okay, so the more force you apply to an object, the greater the acceleration of that object will be. We're saying the greater change in its speed, or its velocity technically it will be. So these pictures just kind of show that. If you have a small force of a tiny person or something, I don't know what that is, kicking a soccer ball, you're only going to lead, that's only going to lead to a small acceleration, not a very large change in its velocity. However, if you have a very large force acting on that soccer ball, that will lead to a much larger acceleration. So I'm noticing here that the soccer ball is the same in both cases, so this is the same amount of stuff that force is acting on. So yeah, essentially they're proportional to each other. Which is what this slide's all about, right? So you can say that the acceleration of an object goes as, or is proportional to the force on that object. And you remember, technically net force. All the forces together, the equivalent of all those forces acting is one direction of force. Yeah, so being proportional, these are just examples of what it means to be proportional. If you double the force that you're applying to an object, you're going to double the acceleration that object experiences. If you triple it, you're going to triple the acceleration. If you apply half the force, then you're going to only get half of the acceleration for that object. And so the arrows go both ways, right? Because if an acceleration of an object is doubled, then you can infer that the force on that object is doubled. Okay, so how about a quick little check on yourself here. Say you're pushing a crate with 100 newtons of force. If there's a force of friction between the crate and the floor, and that force is 100 newtons as well in the opposite direction. Remember, friction always pushes against the motion. Does this crate accelerate? And then after that, does that also imply that the crate is not moving? Or is it moving or is it not moving? So go ahead and just pause the video for a second and jot down an answer for each of these, hopefully. Okay, so for the first question, hopefully you said no, the crate's not going to be accelerating because the net force on the object is, well, 100 newtons this direction, 100 newtons that direction, opposite each other. So they essentially cancel each other out. You get zero net force, which means no acceleration. So does that mean that the crate is not moving? No, it doesn't necessarily mean the crate's not moving. So all that tells us is that the object is not accelerating, meaning it's not changing its velocity. So if the object could be moving at a constant speed. It also could be not moving too, but it doesn't necessarily imply that this crate is not moving. Okay, so we gotta try to make a distinction here, because the next part we're leading up to Newton's second law, and part of it is about force and acceleration. The other part of it has to do with mass. So people often confuse the terms mass and weight. And if you think of mass is literally a measurement of how much matter is making up an object. So we're going to talk more when we get to the atomic nature of matter, what matter is made up of. But you've probably already heard that normal matter, like us, the air, the water, all that stuff is made up of atoms. And those atoms are made up of protons and electrons and neutrons. That's one level of understanding of it. And essentially, mass is basically a measure or a count of how many atoms or how many protons, electrons, and neutrons is making up that object. So I myself, well, it's billions and billions and billions and probably trillions and trillions of atoms that make up my body. Right? And that amount of atoms is a certain amount of mass. Right? So it doesn't matter if I'm standing here on the Earth, if I'm floating in outer space, if I'm standing on the moon, if I'm right near the sun, it's the same amount of matter that's making me up. So I have the same mass everywhere in the universe. Yeah. However, my weight will vary depending on where I am, depending on how large the gravitational field I'm in. So our weight is actually a measure of the force of gravity pulling us down. So I have a certain amount of mass, and here on Earth, right at the surface of the Earth is pulling me down with a certain amount of force, and that results in, as I showed you maybe last time, an acceleration of 10 meters per second. And also, as I said last time, there's a normal force, or support force, we call in this class, that's pushing back up from the floor onto me. Right? And it's that support force that causes me not to go through the floor. So your weight is really an experience of essentially gravity pulling you down and the support and the floor pushing you back up. So you feel that the balance of those forces. So weight is essentially a measure just the force of gravity on an object. And since the force of gravity can change depending on where you are, like if I'm on the Earth's surface, it's one thing. If I'm on the moon's surface, looks like maybe like a sixth of the Earth's gravitational pull, right? Or a sixth of the Earth's gravitational field strength. Right? So the pull of gravity, or the force of gravity on the moon, is much weaker than the force of gravity on the Earth. If I were right next to the sun, the force of gravity is much stronger, much more massive. If I was floating in outer space somewhere and there's essentially no gravitational pulls on me, then I would be weightless. Right? So weight is something that can vary from place to place depending on the situation. Mass does not vary, which is one of the main reasons why in physics we don't generally worry so much about the weight of an object as the mass of an object. So, because it's something that just doesn't change. It doesn't care where you are. Yeah, so mass is this universal property, but weight depends on the force of gravity that you're in, or the gravitational field you're in. And yeah, as is shown in here, the weight of a person, maybe if they're 120 pounds, on the moon they would weigh only about 20 pounds, because the moon's gravitational pull is about the sixth of the Earth. Yeah. Oh, so a couple of other things. So mass, since mass is so this immutable amount of stuff that you're made up of, and it is a way or a measurement of the inertia of an object. So remember, inertia was just the tendency of an object to not want to change its motion. And I told you before that inertia is proportional to the mass of an object. So that's another way of saying that mass is essentially a kind of a measurement of the inertia of an object. And that doesn't change. The unit we use for mass, at least the metric unit, is a kilogram. So it turns out that in most of the world, they use kilograms as a measurement of their mass, but also a way of telling somebody how much they weigh, which is a little bit misleading. But it's much more universal to say that I'm this many kilograms than it is to actually say I'm this many pounds, right? Because pounds is actually a measurement of force, right? So the unit of force that we used most last time, I think, was a Newton, and a Newton is the metric unit of force. But here in the United States, we don't use the metric system, and a pound is the unit for force. I think I mentioned that last time as well. So, don't worry too much about the unit stuff again. That's not super important, but it might help keep things straight if it makes sense to you. that we have a difference between a kilogram. And I think actually in our system there is a term for mass, but nobody ever uses it. I think it's a slug. I don't know exactly. Okay, so there you go. So mass and weight, two different things. They're related, but only because the force of gravity and your mass determines your weight, right? Okay, so why is that important? Well, like I said, mass comes into Newton's second law too. And as it turns out, if you're applying a force to an object, and you apply the same amount of force to different objects, say I apply 10 newtons of force to whatever objects, if that object is a very small mass, it's going to lead to a very large acceleration. Right? That force, that 10 newtons of force acting on an object, is going to lead to a pretty large acceleration. Versus if I apply 10 newtons of force to a much larger mass, it's going to lead to a much smaller acceleration. So hopefully you recognize this as the other sort of relationship I told you about, and that is an inversely proportional relationship. So it turns out that mass and acceleration are inversely proportional to each other. Alright, so as we would just show here, acceleration is proportional to 1 over the mass, or acceleration is inversely proportional to the mass, as we'd also say. Or one other way of saying is acceleration goes as the inverse of the mass. So examples of that are if the mass of an object is doubled and the same force is being applied, then the acceleration will be cut in half. Double the mass, divide that acceleration by 2. If the mass is tripled, then you only have a third of the acceleration. And again, this is imagining the same amount of force being applied to these different masses. If the mass is halved, right, if you have a smaller mass by factor of 2, then that actually implies that there's a doubling of acceleration, or the acceleration will be double what it was for the same force. Alright, so another question for you. So in all these examples, we just want to imagine that there's a brick on some kind of surface, and fortunately there's no friction between the brick and the surface, so just imagine it's going to slide very smoothly, and your hand is going to apply a certain amount of force depending on what's written in each of the different options, and that force is going to accelerate the brick. Right? So when you apply this standard force to one brick, you get a certain acceleration, right? So think of that as like that's our beginning acceleration. And each of these other questions, you want to be able to answer how many times more or less will these other situations be accelerated by, or what will the acceleration be related to that first one. So in all the pictures, either the force is what it says, the masses are these bricks, and each of those bricks is the same mass, right? So in the top two, it's the same brick. In the first one or the middle left one, there's 2 bricks, so twice the mass. In this one, there's still 1 brick. The bottom left, there's 3 bricks, so 3 times the mass, right? That's right. So yeah, so take a minute and see if you can answer these, or give some kind of answer. Again, don't worry if you're wrong. Sometimes it's better to be wrong because you probably remember why later on. Okay, so let's just go through these. All right, so the second one down on the left here, if you're applying the same force and you're doubling the mass, there's 2 bricks now. Remember, the acceleration is inversely proportional to the mass. So if you double the mass, you get half of the acceleration. It's going to accelerate half as quickly. If you go to the next one to the right in the middle here, if you apply twice as much force, remember acceleration is proportional to force, So twice the force means twice the acceleration. And then the bottom left here, 3 times the mass, 3 bricks, 3 times the mass means 1/3 of the acceleration, or 1/3 as much acceleration. And then finally, if you double the mass, but also double the force, then those effects are essentially cancel each other out, and you're going to get the same acceleration. You could also think about it as, you apply twice the force, that would say you get twice the acceleration, but you also double the mass, which means you cut that back in half. So you end up with the same acceleration. All right, and that leads us to Newton's second law, right? Because pretty much all that stuff about acceleration and force, acceleration and mass, that's all that there really is to Newton's second law. Newton's second law says the acceleration is proportional to the force applied to an object. It is inversely proportional to the mass of that object. And finally, acceleration only depends on the force, remember still net force technically, and mass of an object. So if you put those two relations together into an equation, that's all that's in the equation, that's what you get. Acceleration equals the net force divided by the mass. And yes, so just like force is a vector quantity and velocity is a vector quantity, acceleration is also a vector quantity, meaning it has an amount or a magnitude and a particular direction. And if you're wondering what acceleration or what direction an object will accelerate, well, the direction comes from the net force on that object. So whatever the net force direction is from, when you're applying when you're pushing on a brick to slide across the table, the net force you're applying is in that direction, the acceleration is also in that direction. So whatever net direction the net force is, that's the same direction as the acceleration. Cool. So let's see some demonstrations of Newton's second law in action here. As it turns out, a lot of these ideas are, as I kind of pointed out before, sort of ideal situations, like if we don't have to account for air resistance, friction, and that kind of stuff, then these laws apply very nicely and easily. They're still true when there is friction, there is air resistance. It's more complicated because you then have to take into account the force from friction and from air resistance, and that can be somewhat fairly complicated actually. So, as it turns out, in space or in free fall, technically they're in free fall here, you don't have, you don't feel the weight, and things just float around, and there's very little air resistance for the most part. Maybe not any less than it would be here, but being able to float freely, they can just kind of push objects and see what happens to them. So these are videos, and there's a bunch of these videos they made from the International Space Station, which are really useful and educational. So we're going to utilize them. So basically what they're going to do in this video, what he's going to do is he has this elastic band that's tied between the two walls here. He's going to take different objects and basically use the elastic band to sort of like slingshot them. And in order to keep the same amount of force applied on these different masses, right? Because we just want to see what happens to the acceleration of an object when you apply the same amount of force, but you change the object to be different amounts of mass. So to keep the same force, you just take this elastic band and he pulls it back the same distance each time, so that when he releases it, it applies the same amount of force to these objects regardless of the mass of the object. So I think he's going to start with a pretty small object and start moving up. Yeah, so a small mass, a little piece of chapstick. So we take that band, pull it back to this kind of stopper. Oh, and shoots it off. Accelerates very quickly, it gets up to a very high rate or high velocity. So this guy a little bit more mass. It's a model of a lander or something. The same force didn't accelerate nearly as much. And then finally we go to this big mass bundle of foam or padding or something. But again, still applying the same amount of force to these objects, just using this band pulled back the same amount. And very little acceleration, right? Almost looks like a tanker slowly taking off from harbor or something. So yeah, so there you go. There's a demonstration of the same amount of force being applied to increasing amounts of mass, and we see that the acceleration of those masses goes down. So that was a demonstration of the acceleration of an object being inversely proportional to the mass of that object. So let's do a little sort of calculation here, having to do with the weight of objects. So like I said, weight is different than mass because weight combines how much mass an object has along with the force of gravity that's acting on that object. So, like I told you before, the acceleration of Earth's gravity, at least near the surface, is just about 10 meters per second per second. So if we take Newton's second law and rearrange it slightly by essentially multiplying both sides of that equation by this mass, then we end up with this version of Newton's second law, which says the force on an object is equal to its mass multiplied by the acceleration that object is experiencing. So, I've been telling you that the force, gravitational force on an object is its weight. So, if you have a 1 kilogram mass, hunk of something, it's a kilogram of amount of protons and electrons and neutrons, then the force, the gravitational force of that mass is going to experience is equal to that 1 kilogram, the mass, multiplied by the acceleration that it experiences due to gravity, right? 10 meters per second per second. So 1 kilogram times 10 meters per second squared is 10, the number 10. And newtons is our unit of force. Again, don't worry too much about units, but it turns out that a newton is just a kilogram times a meter divided by seconds squared, 2 factors of seconds. So you take 1 kilogram, you put it on a scale, it's going to tell you that thing weighs 10 newtons. At least right here on Earth, right? You take that 1 kilogram up to the moon, it's going to tell you it weighs about 1/6 of a newton. So, again, well, further demonstration that the weight of an object really depends on the acceleration that object experiences, and it's and most of the time, weight is a measure of just the gravitational force on an object. But if you accelerate that object in a different way as well, for instance, if you have you're in an elevator and that elevator starts moving upward or starts moving downward, right? Then the elevator has started from no motion and it goes to speed up to some velocity, however fast it speeds up, right? So it's changed its velocity, it is accelerating, right? So you kind of combining the acceleration of that elevator and the acceleration due to gravity, and you can change what the measure of the weight of that object is now. So, right, so we take that 1 kilogram object, just some hunk of metal or iron or something, and if you're in an elevator and you're holding a scale, like a hanging scale, you hang that weight on, you're not accelerating beyond the acceleration of gravity, the scale is going to read 10 newtons, right? Like we just saw last time. 1 kilogram 10 newtons because the acceleration of gravity is about 10 meters per second. However, if you start accelerating upwards, then essentially the acceleration of the elevator going upwards kind of combines with the acceleration or the force of gravity, and you probably know this, you experience this feeling when an elevator starts moving upward. For a moment you feel heavier than you normally do, right? It feels like you're being pushed into the floor because your weight has momentarily kind of increased. And that's exactly what happens. That acceleration adds together, and in the end we would actually measure, well, if you were going up add another half of gravity's acceleration, or half of what gravitational acceleration is, then we'd add basically half to the weight. So the total acceleration of this object is now 15 meters per second squared. So 15 meters per second squared times 1 kilogram, 15 newtons. So you can measure a weight of 15 newtons. And then the opposite case is true if you go downward. Again, imagine you're on that elevator. When it first starts to drop downward, you almost feel lighter for a second. You do feel lighter for a second. And that is because that acceleration is canceling out, in a way, gravitational acceleration. And if, if you're going down, accelerating downward at half of the acceleration due to gravity, then you'd end up measuring a weight that's half of what it normally is, just under gravity's acceleration. And finally, if you're accelerating downward at 10 meters per second squared at the acceleration due to gravity, well, that means you're just in free fall, right? It's basically like the elevator chain just broke and all the safety mechanisms on an elevator failed. There are many safety mechanisms on elevators, by the way, but all of them all of a sudden failed and the whole box just drops down. In that case, it's just like, you just like jumped off of a cliff or something, or you jumped out of an airplane. You're in free fall and you don't feel any weight at all. Okay. So what happens to objects, I guess, in free fall? Or why is it now that the acceleration of gravity doesn't care how much mass it's trying to accelerate? Is another way of looking at that. So if you say you take a brick and it has a mass of m, whatever that m is, maybe it's a kilogram, and you drop that brick, then gravity is essentially pulling on all the mass that makes up that brick. Right? So remember, I guess we haven't gotten to that yet, but we'll talk about gravity more later, and essentially whatever it has mass pulls on other things with mass. Right? So that brick is made up of mass, the Earth's made up of mass, and the gravity is essentially the Earth pulling that mass to it. Okay, so you have that force of gravity pulling down, it's on all that mass, that amounts to an acceleration of 10 meters per second squared. Right? And g is what we use, little g is what you use shorthand for the acceleration of gravity. That just means 10 meters per second squared, or per second. Alright, so we have that one brick. Now imagine you double that mass, you put a second brick on there, so you have 2m, twice the mass. Well, now there's also twice the mass, or that matter for gravity to pull on, so it actually pulls with twice as much force. So you doubled the mass, you doubled the force on that object, and in fact, since the acceleration of the object is proportional to mass, or proportional to the force, inversely proportional to mass, when you double the force and double the mass, you still wind up with the same acceleration. So, in a sense, Newton's second law is one way of understanding why Galileo was correct that it doesn't matter how much an object weighs or the mass of an object, it's going to fall at the same rate. Assuming air resistance isn't that big of a deal. We'll talk about air resistance a bit at the end of this lecture, actually. So in a sense, it really comes down to the ratio of the force on the object, the weight of the object, and its mass that will tell you the acceleration the object is going to experience. But if you're doubling the mass of the object, then you're doubling the force on that object. So you're doubling the weight of that object, which means you get the same gravitational acceleration in the end. And I guess this is sort of similar to the concept or the fact that for a circle, the diameter of the circle, how wide across that circle is very much related to the diameter of that circle, the circumference of the circle, the distance around the edge of the circle, such that if you increase the diameter, you stretch that circle out, the circumference increases by the same amount. So if you double the diameter of a circle, the circumference doubles as well. And such that the circumference divided by the diameter always equals pi. That's why pi is such a special number. It doesn't matter what size circle you have, as long as it's a perfect circle, you measure the circumference, you measure the diameter, you divide them, you get pi. So same sort of idea in that when the circumference or the diameter increases, the circumference increases by the same amount. And the same idea was with the acceleration due to gravity. When the mass of an object increases, the force on that object, gravitational force on that object, increases by the same amount, so the acceleration remains the same. Okay, so a very interesting demonstration that some of the first, I don't know if this was the first moon landing or one of the subsequent ones, but, well, they just decided to take a hammer and a feather and drop them and verify that Newton's second law is correct, that in the absence of air resistance, those objects are going to drop at the same rate, right? They're going to be accelerated down by the same amount, and that's a slightly slower acceleration because they're on the moon, right? The moon has less mass, it has a lower gravitational pull, but the rate is the same. So in general, if you were just to drop a hammer and a feather, the feather has a very large surface area, it's very light, it actually has a lot of air resistance, and so it will tend to float around a little bit as it goes down, whereas the hammer is just going to drop straight down. But again, that's just due to air resistance. If you take that air resistance away, the moon has no atmosphere, so there's no air there. Drop those two things, bam, they fall at the same rate. So let's see that. We've got the hammer in the right hand, the feather in the left. Drum roll. Maybe I should put the sound on. I don't know what he's saying. Any minute now. There you go. You see them fall exactly together. One more time. Cool. So Newton's second law is correct. The force of gravity on each of those objects is different from the moon, but the mass is also different, right? And they're different in they differ by the same amount. There's maybe twice the force, or probably more than 10 times the force on the hammer, but the hammer is also 10 times as massive. So they both accelerate at the same rate. This might be a good time to point out that the videos on here, they're playing them on the projector and recording them, and maybe doesn't always work out so well. So I always put links to each of these videos, all the demonstration clips in the description of the video, and they're also on the lecture slides. So if you have trouble seeing them here, don't hesitate to just open up a new window and check out the video there. Yeah. Okay, so another demonstration, the difference between, well, essentially a demonstration of the fact that it's really air resistance that changes how some objects appear to fall differently, or they do fall differently on Earth. Why is the case that some objects seem to fall at a lower acceleration than others. And the reason is not because gravity is accelerating them less, it's that there's air resistance that's more, it's a larger factor for some objects, particularly light objects with a lot of surface area, than it is for other objects. So, as an example, if you take a sheet of paper and you drop that sheet of paper, well, the force of gravity is pulling the paper down, and it turns out that air resistance is basically a friction, so it's a force acting against the motion. So as the paper goes down, air resistance pushes up, and since the paper is pretty light, it's not much weight, and that air resistance can actually have a substantial effect on the net force on that piece of paper. So it tends to kind of swish around, not just fall down. However, if you have a book, the book has essentially the same surface area, but its weight is much greater. So the air resistance is about the same on that object, but since the weight is much greater, the air resistance is a much less of a factor. It's much, much less than the weight, so essentially it doesn't really change the overall force. That the net force is still basically its weight, and it drops down at the acceleration of gravity. So just to be clear, that it's not that the gravity is accelerating the paper different than it is the book. And to see that, all you got to do is put the paper on top of the book. It's not attached to it in any way, you just lay it on top of it, and then you release both of them. So in that case, there's no air resistance acting on the paper, and it actually just falls directly with the book, right? The same rate with the book. So there you go, we got the book and the paper separate. The paper, a lot of air resistance, it floats around, takes a little bit longer to fall. Bam. Paper falls at the same rate that the book does. So the only difference between the book falling and the paper falling before was that the paper had the air resistance on the paper was very significant in terms of the weight of the paper. So the net force overall is much less on the paper. Okay, so speaking of air resistance and friction, I think wrap up this lecture with a bit more detail about air resistance and friction. Right? So I've mentioned friction before, and basically I told you that friction is essentially a force, and it's always a force that acts to resist motion. So it always goes against the direction of motion. So for instance, if you're pushing a crate along the ground, whether you're actually moving it or not, that attempted motion in that direction, friction is going to act against that. Right? So maybe it's easier to imagine it. You're pushing it, you're moving along, there's always friction that's pushing the other way between the floor and the bottom of the crate. There's friction that's going to be pushing back, right? So the net force on that object is not just you pushing it because of the friction in the opposite direction. The net force is less than whatever force you're pushing on it with. And air resistance also is essentially, well, it's essentially another form of friction, but in the case of air resistance, it's sort of the friction of an object pushing through the air. Right? So the air is actually made up of atoms, just like everything else is, and when you try to move through those atoms, it takes some amount of sort of force to kind of push them out of the way, and that by doing that, it's essentially there's a resistance to you pushing them out of the way. So the effect of that is that there's always a bit of air resistance that's trying to oppose your motion as you move through the air. And we've all felt air resistance, but you don't think of it as being very much. The air, we don't see the air, so it doesn't seem like there's a whole lot there sometimes. But when you're driving at 60 miles an hour, you put your hand out the window, you feel the air a lot, right? So the air is there, it just turns out that you don't really necessarily experience it unless you're moving through it very quickly or it's moving moving at you very quickly. And that's just like a wind gust, right? So yeah, so friction, air resistance, basically air resistance is just a type of friction, and just like all other friction, it resists whatever motion, or it opposes whatever motion the object is doing. So when this weight is falling down, air resistance is pushing against it. Right? And the same way that when you push along this crate and the friction pushes back, the net force is less than what you're pushing on, because friction is kind of opposing that and canceling some of that out. The weight of an object is also somewhat canceled out by the air resistance, depending on how large the air resistance is, how much force is being applied by the air to it. So friction in general, or what we mostly think about friction is when you're sort of like rubbing objects together. So like in the fast picture, like sliding crates along the ground, rubbing your hands together, your car wheels turning on the ground, spinning a stick in order to make fire. All of that, what that frictional force comes from is actually interactions of atoms and molecules between those two surfaces, right? So atoms and molecules on this surface and atoms and molecules on that surface actually interact a bit when they're close enough, which is why friction only applies or happens essentially when two objects are interacting or touching each other. Yeah, friction is actually rather complicated, as I pointed out before, or mentioned before. Certainly one way of looking at it is it depends on how large the support force is between the two surfaces. So like if I'm standing here on the ground, then again remember there's a support force that's pushing me back up, or pushing against my weight in order to keep me on the ground rather than going through the ground. And if I try to slide along the floor, well, if I don't put much force down on my right foot as I slide along the floor, then there's not a whole lot of friction, right? I can feel the friction because it's still kind of pulling against me or pushing in the opposite direction. However, if I push down on the floor with my foot, right, if I really exert force down, then the normal force on my foot is much bigger now, right? Because I'm pushing down, the normal force balances that out with the same amount of force pushing up. So I increase the, sorry, I keep saying normal force, support force, normal force, same thing. I increase that support force, and now the friction between my foot and the floor is a lot greater, right? I can hardly even move my foot along the floor when I push down very hard. And you can do this too. So the amount of friction between two surfaces depends on the support force between the two surfaces, or from one of the surfaces to the other. And well, I guess the basic properties of friction were first kind of looked at and examined by Da Vinci, which is kind of interesting. There's actually a difference between the friction when two objects are stationary relative to each other versus when they're already moving relative to each other. So the stationary ones we generally call static friction, and in general it's actually greater than the amount of friction when the objects are already moving. The other one, the moving one, we call kinetic friction. And one of the reasons to realize that is that, like this picture here zooms in, surfaces we might think of as being smooth, but all surfaces are actually kind of bumpy and jagged in some way. Very smooth surfaces just have a little bit less of it. Very rough surfaces are much more jagged, big kind of valleys and peaks and whatnot. Right? And when the two objects are stationary, then in a sense the different valleys and peaks and whatnot from the two surfaces have kind of laid into each other, and it's difficult to shift them enough to get them to move apart. Right? So this is the static friction. When the two objects are stationary, you actually have to put a lot of, or the force of friction is quite large, meaning you have to push with a lot of force to get the object moving. However, if the two surfaces are already moving relative to each other, like one's sliding along, then you still have these sort of peaks and valleys and whatnot, but as they move along, they only just kind of fall into each other a little bit, which is what causes that friction. You think about what's causing that friction, that falls in a little bit, so it takes some force to knock it back out. But it doesn't settle all the way in as it would when it's static. So that's why that kinetic friction, or the friction when it's moving, is less than the friction when they're stationary. Okay, so back to air resistance. As I mentioned before, the origin, or the reason that there is air resistance, because the air is made up of atoms and molecules, and by trying to move through those, we have to push them out of the way, and they push back on us. So another term for air resistance is drag, or sometimes called drag force. And yeah, as it turns out, the drag force, or air resistance, is proportional. You don't have to worry too much about the details of this stuff, but it's proportional to the size of the object, the surface area of the object that's kind of crashing through the air, right? Like if I try to run through or just run along very quickly, or bike along rather quickly, I'm going to experience some air resistance. However, if I have a parachute on and I try to bike really quickly, I'm going to get a lot more air resistance, because the surface area is not just me anymore, it's this surface plus the surface of the sort of parachute that's around me. So the drag force is proportional to the size, or the surface of the object that's moving through the air, and also proportional to the speed of the object, right? So that's, again, goes back to, if you imagine biking through the air, then you feel some air resistance. You bike faster, you feel more air resistance, right? So you're speeding up. If you're in a car or you're on a motorcycle and you're going very fast, then you feel a lot of air resistance. Right? So the faster an object moves, the more air resistance you experience, or the larger the air resistance is. Yeah, so again, drag, just like, because it is a kind of friction, drag is actually very complicated. Air resistance can be very complicated. It depends on the shape of the actual shape of the object, how dense the gas or the liquid is that the object's moving through. So air resistance is actually just drag in air. Drag is a more general term that could be like the resistance that you experience as you try to move through water, say. Right? So when you're trying to like run through water, it's very difficult to do, because there's a lot more dense stuff in front of you than if you were just walking, and that causes a lot larger drag on you, so it's much harder to get going. Yeah, and technically drag is only proportional to the speed of an object to a certain extent, and then it's no longer just the speed of the object. So it's rather complicated, but at one level, at a pretty, in a very simplified sort of world, it's just basically, it increases as the surface area of the object that moves through the air increases, and it increases as the speed of the object increases. So here we got that picture again of something falling through the air. The force of gravity is the mass of the object times the acceleration due to gravity. So that's the force, that's the weight of the object being pulled down, and that's constant. The drag force, we could write as, I guess with an R, drag somehow, is pointing the opposite direction. It opposes the motion of this object. And so the net force on this object, well, it depends on how large the drag force is, right? Because the force of gravity is always constant, but if the drag force is larger or smaller, the net force is going to, well, it might be downward, it might be smaller, larger. Well, what happens with that? So yeah, so what happens with like the net force on an object as the air resistance changes? So think about, a skydiver, when they jump out of the plane, again, the entire time they're falling, their weight is constant. They have the same amount of mass, the acceleration due to gravity is the same, so it's the same through the whole jump. So the weight, the force of gravity pulling down, is the same. However, when they jump out, they're not moving very fast at first, but the gravity is accelerating that person, so they're speeding up. right? So they start out, they're not moving very quickly, and remember drag is proportional to the speed of the object. So at first, the drag force, the force that's opposing this motion, is pretty small, but as the person speeds up, that force gets larger and larger and larger. Until actually at some point, you're going fast enough that the drag force is increased enough that it's equal to the force of gravity pulling you down. So once the drag force is equal, then there is actually no more net force on you, right? Because there's just as much force pulling down as there is pushing up. So you get zero net force, which means zero acceleration. Yeah, hopefully. That's kind of what this whole lecture was about. Is Newton's second law says that if you have a zero net force on an object, the object no longer accelerates. So right here, once you reach that point, no net force, you're not accelerating, your velocity is not going to change anymore. So this is actually the point where you get to what we call terminal velocity. Terminal velocity, or terminal speed, maybe more simply, right? So that's the speed that you, once you get to that point where drag is just as large as the force of gravity, no more net force, they cancel each other out, no more acceleration, your speed remains the same. Your velocity and speed are not going to change. So that's your terminal speed, or terminal velocity. So why is it, well, if you just jump out of a plane, then you're going to have a very high terminal velocity. The reason being that the speed that you need to get up to in order to have the same, in order for the drag to balance out friction, that speed is going to be very large. However, once you open up your parachute, remember again, drag is also proportional to the surface area of the thing that's moving through the air. So you open up a parachute, you have a very large surface area now, right? So right as you open your parachute, there's a huge increase in the drag force on you. So a huge increase in the drag force means that now, gravity again, constantly pulling down the same amount, right? But now your drag force just shot up. So what happens right when you pull your parachute is you actually decelerate, right? Because there's a net force upward. The drag is much larger than the force down. So there's a net force upwards, which means you're accelerating upwards. And when you accelerate in the opposite direction that you're moving, that's what we call deceleration. So you're decelerating actually. And you decelerate, so you slow down, so your speed gets less, so again your drag force drops back down. And eventually you decelerate enough that your drag force again balances out your weight, and you get zero force, zero acceleration. You've reached your terminal speed now with your parachute open. And that new terminal speed is much, much lower than when you didn't have your parachute open. So this is the reason why, one way to understand why parachutes are very useful, and you should not jump out of a plane without one. Yeah, okay, cool. So that's it for this lecture. And I guess next time we're going to talk about Newton's third law. So I hope you're having a nice day, and I will see you next time.